All right. So now I want to add one more little dimension to things, and that is a lot of times we care about not just the amount of work being done, but the rate at which it's being done. And we define power as the rate of doing work. So if a little bit of work is happening in a little interval of time, dt, then dr dt is nothing more than v, and so the power as the rate of doing work is just the dot product between the force and the velocity. And just dimensions here, force is mass length per time squared. V brings another length and another time, so it's 1, 2, 3, or 1, 2, negative 3. Mass, length squared, inverse time, cubed. Okay, and just for some figures of merit, while you're sitting here breathing, sleeping, whatever it is that you're doing, your basal metabolic rate is about 100 watts. So you're about a 100-watt light bulb. So if you count up how many bulbs there are in here, you can get a sense for either how fast the temperature should be rising or what kind of an air handling system we need. And a horsepower is defined to be 746 watts. And let's see, the average US power consumption is 3 terawatts.
Per year?
No, that's, okay. Perfect, thank you, Ian. Ian says, is that per year?
That says divided by what?
So what's wrong with that question?
Power is already interpreted.
Okay, power is the rate at which you're doing work. Okay, if you wanted to say, how would you calculate the total energy used by?
Terawatt hours.
You could use terawatt hours, or you can see that I've gone the other way. So the total energy consumed, whereby consumed I mean used and converted into a different form, by the people in the United States is about 100 exajoules. That is 10 to the 20 joules. 10 to the 20 joules. And we all know that a year is about pi times 10 to the 7 seconds. So if we divide, right? We knew that? We didn't know that. Pi times 10, it's really 3.16 times 10 to the 7, but close enough. So we divide 10 to the 20 by 3 and change times 10 to the 7, and we get about 3 terawatts.